Hello and welcome you all for Anna University AVU program. So through this program you are going to learn the subject Mathematics 1 fully right from the beginning and to the end of the university syllabus which has been framed from Anna University. Here I am Miss Kripa from Loyola eCamp College of Engineering and Technology, Nungumbakam Loyola campus is going to be with you throughout the course. So as it is being framed in the syllabus, I will stick on to the same schedule. Like we will start with unit 1, that is matrices, and the second unit is going to be sequence and series, like that it goes on. So the first unit 1 matrices consists of topics like eigenvalue, eigenvectors, and Cayley-Hamilton theorem, and reduction of quadratic form to canonical form. So all these three put together is only what your unit 1 matrices is. When we came to know about when we say the word matrices itself, it says that it is very simple to us, and we had been studied many things about matrices in our lower classes, and about the types and other things, properties, we have already discussed in bridge courses which has been conducted in all the colleges, and it has been framed again by Anna University. It is the curriculum, one of the curriculum in the Anna University syllabus. So let us go into let us recall the types of the matrices before we get into unit 1. The actual topic of the unit 1 starts with eigenvalue and eigenvectors. So before we get into the actual topic, we list out the types of matrices. I'm not going to go in much deep or brief about the types. We'll quickly list out what are the types, and in 1 or 2 words I'll give you some notes about how it is being explained, and we can get into our main topic, and we'll do much more in eigenvalue and eigenvectors. So here we start. It is that we are going to start with unit 1 matrices. So defining about matrices, that everybody knows. We had been right from the schooling, we had been studying about matrices. So we know that matrices is nothing but a set of mn elements which is arranged in a rectangular form. It consists of some m rows and n columns. How do we represent this? As capital A, set of all elements like A, I, J, where I varies from 1 to etc. up to n, and J varies from 1, 2, etc. up to n. So this is about how do we define matrices. Regarding the types of matrices, there are many. We can list out many types. The first is a row matrix. Column matrix, square matrix, diagonal matrix, triangular matrix, here we have lower triangular, and upper triangular, so let us in 1 or 2 words we'll take about these types. and then we'll add some more among the types of matrices. Row matrices is nothing but which consists of one row, and column matrix which consists of only one column, and square matrix is where you have equal number of rows and columns. All these things we have learned, so I am not going to give you much brief about it. Equal number of rows and columns. What do you mean by diagonal matrices? Is we have only the main diagonal elements, and the rest of it is going to be 0. And the triangular matrix, which is a lower triangular and upper triangular only, we are going to call it as triangular matrix. What do you mean by lower triangular is, we can also give with an example. So it is a low triangular matrix where with above the diagonals, let us take it as 8, it's not 0. So above the leading diagonal we will have elements, entries with non-zero values, and below the leading diagonal it will be 0. So that is lower triangular, and upper triangular will be like this. So let us have the diagonal entries 1, 5, 6, and here it is going to be some 4, 2, 1. This is going to be 0. So like this we can say this could be a lower triangular matrix and this is your upper triangular matrix. We can also list out symmetric matrix, where we are going to talk about symmetric matrix in this unit much about, and skew symmetric, scalar matrix, singular matrix, non-singular, here what do you mean by the symmetric matrices? Even if you interchange your rows and columns, it is going to be same. That is, A set of all Aij would be equal to Aj I. That is, your A transpose should be equal. In that case, we can call the matrix to be a symmetric matrix. When it is skew symmetric is when it is A is equal to minus of A transpose. In that case, we cannot say A and A transpose is same, therefore it is skew symmetric. Scalar matrices is some multiplier would be there, where we call this as scalar. So we can multiply that scalar for all the entries of the matrices. So it is K into A, or this is equal to some B. Here singular matrix or non-singular matrices, here finding out the determinant of the square matrix when it is equal to 0 or when it is not equal to. When it is not equal to 0, we call it a singular. When it is equal to 0, we call that matrix as non-singular matrix. I think types of matrices is enough. We can get into our main topic, that is eigenvalue and eigenvectors. Since about the matrices we have learnt a lot before, this introduction is enough for us to get into the first topic, that is eigenvalues and eigenvectors. It's going to be eigenvalues and eigenvectors. What is eigen? The word is different. It's not like usual word we have been using in mathematics. It is slightly different. What I mean by this eigen is nothing but it's a German word. It's a German word, means proper, or we also can call it as characteristic. So what is proper? It is nothing but to represent this proper is, we call it as eigen. Through this German word only we are representing it as eigen values. What are values? So the proper values we call it as eigen values. Proper values we can call it as eigen values. What are these values actually means is, when we solve the quadratic equation, let us take an example. Quadratic equation of the form ax square plus bx plus c is equal to 0. So solving off this equation, you will get the roots or the values of x. Okay, we are going to name that x as nothing but the eigenvalues. So you may have x1 and x2 as a root. When it is quadratic, you can expect 2 roots. When we solve a cubic equation, you can expect it to get 3 roots, or we are going to call that roots is nothing but eigenvalues, or getting the proper values of a quadratic equation is nothing but eigenvalues. In terms, you can say it is proper values, nothing but eigenvalues. Now how are we going to generate this vectors through this value sets? So any scalar which is associated with a square matrix A, we are going to call it as eigenvalue, and any vector associated with this we are going to call it as eigenvector. In what way it is associated? Let us get into brief. So for every square matrix, let us take A be a square matrix. For every square matrix and a scalar lambda, there exists a non-zero vector. For a square matrix A and a scalar lambda, there exists a non-zero vector. We can represent that vector as capital X. Then this vector is denoted by a row matrix, a column matrix, which consists of n entries. If your matrix A is of order n, then the capital X could be of order n. We have taken a column matrix like this, then such that the association between this can be given as A x is equal to lambda x. So any scalar which is associated with A, we can call it as eigenvalue, and the vector which is associated to that matrix and the value, we can call it as eigenvector. In how are we going to name it as eigenvalue and eigenvector is by this relation. So for a square matrix and a scalar lambda, there exists a non-zero vector capital X. It is non-zero vector capital X, which this is a column matrix, such that A capital X is equal to lambda x. Now this A capital X is equal to lambda, also written as A minus lambda I of x is equal to 0. Now you can call this as homogeneous. It is also linear. So it is linear homogeneous equation in x1, x2, etc. up to xn. We say this capital X is a non-zero vector. In that case, there exists at least one of the elements of the vector should not be equal to 0. Then we say it is non-trivial solution. Then we could say that there exists a non-trivial solution. It's very clear, like this capital X the eigenvector should not be equal to 0, then there exists at least one xi not equal to 0. Only then you could say that there exists a non-trivial solution. Here, getting the characteristic, getting the determinant of A minus lambda I alone. That is how you write determinant of A minus lambda I is equal to 0. When you solve this, you will get an equation in terms of lambda. If we solve it, we will get an equation in terms of lambda, where we could call this as characteristic equation. Where we can call this as characteristic equation. On solving this characteristic equation, your characteristic equation, the order depends on the order of the square matrix. If A is of 2 cross 2 matrix, then the characteristic equation will be of order 2. If A is a 3 cross 3 matrix, then the characteristic equation will be of order 3. You will result. For example, let us take lambda, you can write it as lambda square minus S1 lambda plus S2 is equal to 0. This is possible provided your A is 2 cross 2 matrix. And here this is lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. Whereas if your A is a 3 cross 3 matrix, where this is also a characteristic equation, this is also a characteristic equation, where in turns you get it from determinant of A minus lambda I is equal to 0. The roots of this equation we will represent in terms of lambda. So this lambda is what we call it as eigen values, and the corresponding vector for each lambda, that is, there exists x. How that exists? In terms by the relation A minus lambda I of x is equal to 0. A minus lambda of x is equal to 0. For every eigenvalue lambda, there exists capital X. How it is being? It is like A minus lambda I of x is equal to 0, where you can find what is your capital vector is. So for each of eigenvalue 1, we call it as lambda 1, there exists vector x1, and for lambda 2 there exists vector x2. Like this you can keep on adding it. So now what is the eigenvalues and eigenvectors? It is very clear. The associated scalar with the square matrix, we call it as eigenvalue, and there exists a vector capital X to that, we call it as eigenvector, provided we have an eigenvalue for it. So for each of the eigenvalue we can produce a vector. Okay. This lambda square minus S1 lambda plus S2 is equal to 0 is the characteristic equation. We call this as characteristic equation for a 2 cross 2 matrix. This is nothing but from determinant of A minus lambda I is equal to 0. Determinant of just A minus lambda I is equal to 0. Now provided if your A is 2 cross 2, we get this form. Is it not? In short, we can make it, there is a shortcut method also to find a characteristic equation of this. So we assume the characteristic equation in the form, actually when you solve determinant of A minus lambda I is equal to 0, you get an equation of this form. In turn, you can also get the characteristic equation by a shortcut method. We can assume the characteristic equation as lambda square minus S1 lambda plus S3 is equal to 0. Now, what is this S1, S2 is nothing but the coefficients. Your S1 is coefficient of lambda and S2 is a constant. So, when your A is a 2 cross 2 matrix, you can define S1 as sum of the main diagonal elements. Sum of the main diagonal elements in A. And S2 is very simply, it is determinant of A. It is simply S2 is determinant of A. So by finding S1 in this form and S2 and substituting in this place, you will get the exact characteristic equation of the respective square matrix. So this is the other way of getting it. If it is for a 3 cross 3, in short, how could you find the characteristic equation is? We will assume the characteristic equation is, since it is 3 cross 3, we will end up with an equation, it's a cubic equation. So lambda cube minus S1 lambda square plus, it's not clear, minus lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. When you look at the cubic equation, see, here we started with the lambda cube, then the coefficient of lambda square, we are taking it as minus S1 and S2, and finally it is with S3 negative sign. Here you can define or you can find this S1, S2, S3 by, now S1 is going to be same as it is for a 2 cross 2 matrix. It is sum of the main diagonal elements of A. You are going to sum up all main diagonal elements of A, and S2 is sum of minus of A. Okay, sum of the minus of the main diagonal of A, and S3 is determinant of A. I'll show you with how to find the characteristic equation in this method by taking a problem. So now it is very clear, like how do we find the characteristic equation, that is by A minus lambda is equal to 0. It's very clear that how do we find the characteristic equation, that is A minus lambda I is equal to 0. That is, well, in particular it is determinant of A minus lambda I equal to 0. And here you can call this determinant of A minus lambda I alone as, if this is characteristic equation, and here this is called characteristic polynomial. This is called characteristic polynomial. We don't say it is equal to 0, so we call it as characteristic polynomial. The roots of this equation, it is eigenvalues. How are we going to name it? Lambda 1, lambda 2, lambda 3, etc. And the corresponding vector, we are going to call it as capital X1, X2, X3, etc. Okay. So if it is a 2 cross 2, you will end up with a quadratic equation. If it is a 3 cross 3 matrix, you will end up with a cubic equation. We should know how to solve the quadratic equation and cubic equation. So quadratic equation, either you can solve it by factorizing or by the quadratic formula like minus b plus or minus root of b square minus 4ac by 2a. How do I solve cubic equation? And by the first root you can use it by, you can find it by trial and error method, and the remaining roots by synthetic division or by factorizing. Okay. So all this we had been learnt in a lower classes of finding the roots of a quadratic and cubic equation. So I am not going to do much about it. Straight away we can get into the problems. So before we get into a problem, we will also know about what is linear combination. What have we learned so far? We started with eigenvalues, eigenvectors. So through finding the characteristic equation of a square matrix with a relation, we could find values and we could find vectors. Here, how do we define the linear combination is, for, let us take some vectors like x1, x2, x3. Maybe in some cases finding the eigenvalues and eigenvectors, we may come across this linear combination of definitions like linearly independent and linearly dependent. So better it is that we introduce now, and later on we can use the definitions over there. If capital x1, x2, x3, etc. up to xn are set of vectors, let us take it. Set of vectors, and we'll take some scalars like alpha 1, alpha 2, alpha 3, etc. up to alpha n. Then how the combination of this scalars along with the vector, it is alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus etc. is equal to, this is called linear combination, plus etc. just adding on, we call this as linear combination of the vectors like x1, x2, etc. up to xn. Here, following the linear, followed by linear combination, we have linearly dependent vectors, and we can call the vectors as linearly independent vectors. Independent vectors. What is linearly dependent and linearly independent is? Linearly dependent the other is linearly independent. The vectors as x1, x2, etc. up to xn, we take a set of vectors. Then there exist scalars saying alpha 1, alpha 2, alpha 3, etc. such that the linear combination, that is alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3, like this linear combination should be equal to 0. This linear combination should be equal to 0. In that case, we can say the vectors to be linearly dependent. Here, for linearly independent, it is nothing but you could find out from the word itself, it is dependent here, it is independent here. If it is not dependent, then finally land over with independent vectors. Here you can say this alpha 1 x1 plus alpha 2 x2 plus etc. up to alpha n xn is equal to 0, which implies saying this alpha 1 equal to alpha 2 is equal to alpha 3 is equal to 0. Okay, where you can say this alpha scalars are all equal to 0. Here, in that case, we say the linear combination is equal to 0. Here also we say the linear combination is 0, provided here this alpha are all 0. Here this alpha are not 0. All these alphas are not non-zero. Now it is very clear. When do we say it is linearly dependent, and when do we say it is linearly independent? So this linear combination is equal to 0 provided there exist non-zero scalars. Here you can say the linear combination is 0 provided this alphas, the scalars are all equal to 0. Maybe this linearly independent and independent concept we will use in eigenvectors. When do we say a sectors? When do we can say a vector set of vectors to be linearly dependent? Is that just now we have been saying, and also we can define orthogonal vectors. When do we say a vectors to be orthogonal? Let us take set of vectors like x1, x2, etc. or let us define for just two vectors. When you can say a vectors to be orthogonal, x1, x2, let me take two vectors. When you can say the vectors as orthogonal vectors is when x1 transpose x2 is equal to 0. We say this x2 is orthogonal to x1 and x1 is orthogonal to x2. In that case, x1 transpose x2 is equal to 0. Let us take some more vectors like x1, x2, etc. up to xn. In that case, when you can say that it is mutually orthogonal, x1 is orthogonal to x2, x2 is orthogonal to x3 is nothing but we call it as mutually orthogonal to each other. Mutually orthogonal. In that case, this xi transpose xj is equal to 0 for all I and j, where I is not equal to j. Okay. So now we know what is vectors, what is values, what is vectors, where do we get the eigenvalues is from the characteristic equation, and what is characteristic polynomial we have seen, and how to express a linear combination, and when that linear combination could be said as dependent and when it is independent, and when a set of vectors said to be mutually orthogonal, and when it is when you can say the set of vectors are mutually orthogonal is by the previous condition where xi transpose xj is equal to 0. Now we can start with the problem finding out the characteristic equation, eigenvalue and eigenvector. I will show you for a simple 2 cross 2 matrix, then we can start doing with a 3 cross 3 matrix. Let us take a matrix, simple matrix like 1, 2, 3, 4. I just randomly numbered the matrix. So the order of the matrix is 2, it's a square matrix. Okay, it should be a square matrix, only then we can define the characteristic equation and then we can find the eigenvalues. Here it is a 2 cross 2 matrix where how do you find the characteristic equation? It is by A, determinant of A minus lambda I is equal to 0. I will show you in both the methods to find the characteristic equation. Then we use always the shortcut method. What will be your I? It is 1, 0, 0, 1. In case then what will be your lambda I? Lambda 0, 0, lambda. So A minus lambda I could be 1 minus lambda 0, 3, it is 4 minus lambda, it is just 2 here. 1 minus lambda, 2 minus 0, 3 minus 0, 4 minus lambda. So finding the determinant of A minus lambda I is equal to 0, that is determinant of 1 minus lambda, 2, 3, 4 minus lambda. As you have learned to find the determinant of the matrix and all in your lower classes, I think I don't need to teach separately for you. So when we multiply, when we find the determinant, it is 1 minus lambda into 4 minus lambda minus of this is 6. So as we simplify this, 1 minus lambda into 4 minus lambda is equal to 6 minus 4 minus lambda minus 6 is equal to 0. It is 4 minus, when you multiply it is minus of lambda minus 4 lambda plus lambda square minus 6 is equal to 0. Or in turn you can put it in order, lambda square minus 5 lambda minus 2 is equal to 0. Now we get the characteristic equation of the matrix 1, 2, 3, 4 as entries. Now in shortcut method, we can make it very short by assuming the characteristic equation by knowing the order as lambda square minus s1 lambda plus s2 is equal to 0. Now how do you define this s1? By sum of the main diagonal elements. And how do you define s2 is getting the determinant of A. Okay, so let us sum up the diagonal elements. it is 1 plus 4, it is just 5. You can make it very simple saying your S1 is 5. And getting the determinant of A, it is 4 minus 6. It is 4 minus 6. So what do you get? It is minus 2. So how do you write the characteristic equation? We already assumed in the form of lambda square. What is your S1? It is 5. We have a minus sign in the formula itself. So minus 5 lambda plus your S2 is minus 2. Therefore, it is minus of. It's plus in the formula. Here it is minus. It is minus 2 is equal to 0. Or how do you write it? It is lambda square minus 5 lambda minus 2 is equal to 0. Now this is called characteristic equation. See, through the determinant of A, through finding determinant of A minus lambda, it is quite lengthier. Even though it is simple, it is quite lengthier. In order to save time, we can use this shortcut method where you can find the characteristic equation by getting the coefficient of this lambda called S1 and the constant as S2. Similarly, you can also define for 3 cross 3 matrices. So in any way, we will always try to find the characteristic equation of determinant of A minus lambda I by the shortcut method, where you can save time and you can do it faster also. Consider a 3 cross 3 matrix. We are going to find the eigen values and eigen vector for this problem. Okay. Before I could start the problem, I wanted to mention about the symmetric and non-symmetric matrix which we have discussed earlier. What I mean by symmetric matrix is if A and A transpose equal to, if A and A transpose are equal, we could say the matrix is a symmetric matrix. If A is not equal to A transpose, then we say it is non-symmetric matrix. Here let us check whether it is A and A transpose are equal. If I find A transpose, then it is 11, 7, 10. It means I have interchanged the first column as row, first row, then the second column as second row. Now, is it my A and A transpose are same? This is A. Is it my A and A transpose are same? It is not. Okay. The first column is with 11, 7, 10 and it is 11 minus 4 minus 7. So we say here it is not equal. So this problem comes under non-symmetric. Actually here we have 4 cases where non-symmetric matrix and symmetric matrix. We name the matrices with non-symmetric and symmetric. Here under symmetric we have repeated roots, non-repeated roots, and here also we have repeated roots, non-repeated roots. Into much detail about the repeated and non-repeated roots we will talk later. Now let us take the same question to find the eigenvalue and eigenvector. It is 11 minus 4 minus 7. What's the second row? It is 7 minus 2 minus 5, and it is 10 minus 4 minus 6. How to find the eigenvalues? First, by knowing the characteristic equation. On solving of the characteristic equation, we get the eigenvalues, and for every eigenvalue there exists a non-zero vector. Through that we will find what is the eigenvector is. So the first step could be finding characteristic equation. So how do you find the characteristic equation is? So by finding the determinant of A minus lambda, it's going to be quite a big process. So we use the shortcut method of finding, that is lambda cube minus S1 lambda square minus it's plus S2 lambda minus S3 is equal to 0. Now how do we find S1? Is by sum of the main diagonal elements of the matrix A. This is nothing but your A is. So as we sum up, what do we get? It's 11 minus 2 minus 6. So it is 11 minus 8, it's going to be 3. Now getting the S2, it is finding S2 is defined as sum of the minor matrix of the main diagonal. Which are the main diagonal entries here? It is 11, minus 2, minus 6. So finding out the minor matrix of the main diagonal elements is leaving off the corresponding row and column of the first diagonal element, that is 11, you get minus 2, minus 5, minus 4, minus 6 plus, then leaving off the second row, the corresponding entry, the entry for the second diagonal element is minus 2, leaving off the corresponding row and column, we get 11, minus 7, 10, minus 6 plus, and the third diagonal entry is minus 6, it is 11, minus 4, 7, minus 2. Getting the determinant of this, it is going to be minus 2 into minus 6 is 12, minus 20 plus, here it is minus 66, minus into minus plus, that is 70. Here we have a negative sign, so it is plus 70, minus 22 plus 28. So summing up this, you get it is minus 8 plus 4, this is plus 6. So what is your S2? S2 is 2. Now let us find S3 by finding the determinant of A. Determinant of A, let us calculate. It is 11 into minus 2 into minus 6, that is 12, minus 20, minus into minus plus 4. As we find the determinant, we have a negative sign there. Therefore, corresponding row and column, if you take off, you will get minus 42 plus 50, minus 7, minus 28. Multiplying this 4 into minus 4 is minus 28 plus 20. Now simplifying further, we get 11 into minus 8 plus 4 times of 8 minus 7 into minus 8. Let us simplify further. You get minus 88 plus, this is 32, minus into minus plus 56. So it is equal to, you have 88, so it is 0. Determinant of A is going to be 0. What is my value of S1? It is 3, and the value of S2 is 2, and S3 is 0. So let us put this in the characteristic equation form, which we have assumed. Lambda cube minus 3 lambda square plus 2 lambda equal to 0, because S3 is 0. Lambda cube minus S1 is 3 plus S2 is 2 minus S3 is 0. So what do you mean by this S3 is 0? It means the determinant of A is 0. So whenever you have a determinant of A is 0, you can also find like one of the eigenvalue would be 0. By taking lambda as common, we could get this as lambda square minus 3 lambda plus 2 is equal to 0. So could you able to understand now? Where lambda, one of the eigenvalue, it's going to be 0. You are solving off this lambda square minus 3 lambda plus 2 is equal to 0 will give you 2 more eigenvalues. So this is what it is, lambda minus this 3, but while factorizing you can get this as lambda minus 3 lambda. It's lambda plus minus 3 lambda or we'll write it in terms of its roots. So whenever it is equation of order 2, what do? Either we factorize or we'll find it through quadratic equation formula. So we'll check whether it could be factorized. So here it is minus 3 we have, and the product of 2, and here the coefficient of lambda square is just 1. So 2, you have to write it in such a way, by adding it, by multiplying you have to get 2, and by adding you have to get minus 3. So we'll check whether that is possible for factorization. Lambda square minus 2 lambda minus lambda plus 2 is equal to 0. In that case, you will have lambda minus 2, and taking minus 1 as common, this is lambda minus 2 is equal to 0. So see, when you multiply this minus 2 into minus 1, you get plus 2, and when you add, you get minus 3. So the roots of this quadratic equation is 1 and 2. Therefore, putting everything together, lambda is equal to 0, 1, 2 are the characteristic roots. When we have the roots of a characteristic equation, when we have the roots of the characteristic equation as eigenvalues, then we could find the eigenvectors corresponding to these values 0, 1, 2 separately. Okay. What are the values now? 0, 1, 2. Let us find the eigenvectors. In order to find the eigenvectors, let us take the relation A minus lambda I of x is equal to 0. Fine. So, what is A minus lambda I? Let us find. It is going on to the previous pages. It is 11 minus 4 minus 7. This is minus just 7. Minus 2 minus 5. 10 minus 4 minus 6. Minus 2 minus 5. 10 minus 4 minus 6. Okay, minus lambda times of identity matrix. Identity matrix should also of 3 cross 3 matrix. So let us take identity matrix of this kind: 0 1 0 0 0 1 of x. So this is as a whole of x is x1, x2, x3 is equal to 0 0 0. Okay, let us rewrite this. It's 11 minus lambda. When you subtract these two and operate on x1, x2, x3, we get this A minus lambda of x is equal to 0. So you will have changes only in the diagonal entry. See, it is 11 minus lambda. It is minus 4 minus lambda times of 0. So I will write the matrix A minus lambda is 11 minus lambda. No changes with the rest of the entries than diagonal. So it is 7 minus 2 minus lambda minus 5, 10 minus 4 minus 6 minus lambda of x1, x2, x3 is equal to 0 0 0. You can very well name this as equation number 1, or you can number it, or you can name it like this. Then what is this lambda? Lambda has 3 values saying 0, 1 and 2. So each of the eigenvalue we have a vector x1, x2, x3. That is what we have discussed earlier. So let us find the corresponding vector for the values 0, 1, 2. So as we substitute lambda as 0 in this form, in this equation 1 which we have done. Now why are we doing all these things? To find eigenvector. We already found values. Now we have been finding eigenvector. Okay. As we substitute lambda equal to 0, we get, taking lambda is equal to 0 in first equation, we get 11 minus 4 minus 7 minus 4 minus 7, 7, this is 10, minus 2 minus 5, minus 4 minus 6. Since lambda equal to 0 here, we get the original matrix A. That's why we made it very easy. So by substituting lambda 0 in this place, in this place, in this place, you will get the same matrix A, which is nothing but A. Then x1, x2, x3, which is equal to 0, 0, 0. Now to find this values of x1, x2, x3, now this is what your capital X is. Okay. Let us write the equation in terms of the matrix, which comes out as 11 x1 minus 4 x2 minus 7 x3 is equal to 0, and 7 the next equation is going to be 7 x1 minus 2x2 minus 5 x3 is equal to 0. Last equation is 10 x1 minus 4 x2 minus 6 x3 is equal to 0. Now look at the three equations. You could find that all the three equations are different. It is not identical. If it is identical, we will have some more case to discuss about. Now here it is, since it is not identical, now to find the values of this small x1, x2, x3 by solving these three equations, you can name it as 2. Since already we have equation 1, you can name it as 2, 3 and this is 4. So solving these three equations, when you check the right hand side of this equation, it is going to be 0 here. Okay. So we have a method called cross rule multiplication, where it makes simple to find the values of small x1, x2 and x3. What is this cross rule multiplication is? In order to find the values of the three unknowns, we have three equations. Cross rule multiplication, it is enough if you have two equations itself. So let us consider this 2 and 3. Now listen carefully, then how are we going to find the values? So let me first collect your x1 coefficient, x2. So let us start with x2, x3, x1 and x2 by considering equation 2 and 3. So 2 equations is enough to find the 3 unknowns, so it is enough when it is considered this 2 equation, or 3 and 4 also, or in any order you can take it. Now getting the coefficient of x2, it is minus 4 minus 2, and getting the coefficient of x3, it is minus 7 minus 5. Let us check here, it is minus 5. Okay. And here for x1 it is 11, 7, and for x2 again it is minus 4, minus 2. If you write it in this form, it will be easy for us to get the value of the variables. So x1, we have x2, x3. So finding the determinant of the coefficient of x2, x3, finding the determinant, let us circulate. So let us circle like this, so it will be easy for us to understand. So finding out the determinant of the coefficient of x2, x3, we can give it for the value of x1. So it is 20, minus 4 into minus 5, it is plus 20, minus 2 into minus 7, it is minus 14, or here plus 14, here it is minus 14. And here finding the determinant of this coefficient of x3 and x4, x1 the same order. Let us circulate in this form. So you get finding the determinant. We say it is equal. Okay, finding the determinant is minus 14 plus 55 minus 49. I'm sorry, minus 49 it's minus 49 plus 55 plus 55. And here for x3, getting the coefficient of x1, x2 and finding the determinant of this. If we circle like this, then it is 11, it's minus 22, getting the determinant 22 plus, cross multiplying this, it is plus 28. So let us simplify this further. You get x1 with 6, it is 6, which is equal to x2 by 6 again, and here x3 is also 6. So what is your capital X1? Your capital X1, where it's a vector with x1, x2, x3 non-zero values. It should be a non-zero vector. So we found the values of x1 is 1, x2 is 1 and x3 is 1. Now this is your vector x1 for the corresponding lambda is equal to 0. If you name this as 1, then we can name the vector corresponding vector as x1. Similarly, we have to find out lambda capital X2 for the corresponding lambda 2 and capital X3 for the corresponding lambda 3. Okay. So now how do we find? We can also check this, whether this x1, x2, x3 values are So what is the value of small x1, x2, x3? It is just 1, and x2 is also 1, x3 is also 1. So if you substitute the values of the small variable, the vector, in any of the equation, it should be solved. It should be solvable. Like check, your small x1 value is 1 and your x2 value is again 1 and x3 is 1. So you will get 11 minus 4 minus 7. So minus 4 minus 7 is going to be 11 minus 11. So 11 minus 11 is going to be 0. You can check with the other two equations also. That is what we call it as a solution. Here x1, x2 values, putting it in a column wise, we call it as column vector, or this is your eigen vector. Let us do case 2. When lambda 2 is equal to 1. Okay, lambda 2. So take lambda 2 is equal to 1 in first equation. So what will you get? So as we substitute lambda 2 is equal to 1 in first equation, the matrix, the equation 1 reduced to 11 minus 1. So it is going to be 10. This is minus 4. Actually we have to substitute in this equation. 11 minus 1, it is 10, minus 4 minus 7. Minus 4 minus 7, this is not going to be changed, it is 7. Here already we had minus 2, it is minus 1, it is minus 3. Here it is minus 5. Here we have 10. This is minus 4, no changes with that. Already we had minus 5, now it already we have minus 7, minus 6 we have. So one more, if you subtract with that, you will get minus 7. Okay, now this is into x1, x2, x3 which is equal to 0, 0, 0. Reduce into an equation form. It is 10x1, first row with this column, minus 4x2 minus 7x3 is equal to 0. Then 7x1 minus 3x2 minus 5x3 is equal to 0. Then 10x1 minus 4x2 minus 7x3 is equal to 0. Okay, I am solving this. Now before we could solve these three equations, you can find this first one, second, third to be same, identical. So if shall we number this, it is going to be 2, 3, 4, already it is over, so it is 5, it is 6, it is 7. Now 6 except 6, this 5 and equation 7 are identical. Okay, so when we have such identical equation, what you can do is you can consider that as 1. These two identical equation can be considered as 1. So by considering the two identical equations as 1, considering two identical equation as 1, you left out with now 10x1 minus 4x2 minus 7x3 is equal to 0. The other one is 7x1 minus 3x2 minus 5x3 is equal to 0. It is minus 5x3 is equal to 0. Again, now we have two equations with three unknowns, and both the equations are not identical equations, and all the three unknowns are present here. So three unknowns are present here. If any one of the variables are 0, then we can equate one with the other. Here in this case it is not possible. Again we are going to apply cross rule multiplication. Now as we consider these two equations for cross rule multiplication, we start with giving the coefficients of x2, x1, x3 and again x2. Collecting the coefficient of x2, it's going to be minus 4, minus 3, minus 7, minus 5. Here it is 10, 7. x2 is minus 4, minus 3 and this is going to be x3. This is x3, then x1, then x2. x3 it is minus 7, minus 5. x1 it is 10, 7 and x2 it is minus 4, minus 3. Similarly, now as we have done for the previous case, proceeding of cross rule multiplication, in order to get the value of x1, I'm going to get the determinant of this. So you get 20 minus 21. x1 is going to be 20 minus 21. So let us find what is x2 is. 20 minus 21. Here it is minus. So when we find out, in order to get the value of x2, getting the determinant of the next form, that is coefficient of x3 and x1. So if we circle it, it will be better. And here this is minus 49 plus 50. Minus 49 plus 50. And how are we going to get x3 is, here getting this coefficient of x1, x2, finding the determinant of this minor matrix, it is 30. It is 30 minus 30 plus 28. So as we reduce this, it is x1 by minus 1, x2 by 1 and x3 by minus 2. So what will be our capital X2 is minus 1, 1, minus 2. or this could also be written as 1 minus 1 2. Now this is your eigenvector, corresponding eigenvector capital X2 for the corresponding value. Is the corresponding vector for the value lambda 2 is equal to 1. So similarly we have to do it for lambda 3, that is equal to 2. So let this be case 3 when lambda is equal to 2. So let us take, if lambda is equal to 2 in first equation, again we have to write 11 minus 2. So we have named the first equation as, see, this is what your first equation is. Now we have to subtract 2 for all the entries of the diagonal entries. The remaining it's going to be same. So it is 11 minus 2, it is 9. 11 minus 2, it is 9. It is minus 4, minus 7, 7. Already we had minus 2, so 2 minus 2 minus 2, it's going to be minus 4. Here it is minus 5. Here it is 10. And here we have minus 4. And already it is 6, I think. So yes, it is minus 6. This is what your equation is, minus 6, minus 2. So here it is minus 4, here it is minus 8 you will get. It's going to be minus 8. Now into x1, x2, x3, which is equal to 0, 0, 0. Again, as we are solving this by cross rule multiplication, okay, now we have 9x1, writing it in the equation form, 9x1 minus 4x2 minus 7x3 is equal to 0. Now this is 7x1 minus 4x2 minus 5x3 is equal to 0. Now when you look at all the three rows, it is different. None of the rows it is same. None of the rows is identical. So we have all the three equations as non-identical equation. So let us consider two equations for cross rule multiplication. So again by cross rule multiplication, collecting the coefficient of x2, it is minus 4, and collecting the coefficient of x3, it is minus 7, minus 5. Collecting the coefficient of x1, it is 9, 7, and again we finally land up with x2 again, that is minus 4, again minus 4. So getting the determinant of the coefficient of this is equal to, is it not? So getting the determinant of this, it is 20 minus the minus plus 5 4s are 20 minus 28, and here this one it is minus 49 plus we will have 45 plus 45, and for x3 it is minus 36 plus 28. So x1 is minus 8, x2 is minus 4, and x3 is 8, 6 you have, so again it is 36 to 8 minus 8. In that case, you can write your capital X3 as minus 8, minus 4, minus 8, minus 8, or you can divide throughout with minus 4, you get 2, 1, 2 will be the solution. So now your capital X3 is, 2, 1, 2 for the corresponding eigen value lambda is equal to 2. So we could conclude by stating our result as x1 is 1, 1, 1 is the eigen vector for corresponding lambda is equal to 0. and your capital X2 is, what is your capital X2? It is 1 minus 1. It is 1 minus 1, 2 is the eigenvector for the corresponding eigenvalue lambda is equal to 1, and your X3 is 2, 1, 2 is the corresponding eigenvector for the corresponding lambda value, that is lambda is equal to 2. So this is what it is expected. This is what we had been trying to prove right from the beginning. So we found eigenvalue and the corresponding eigenvector for a square matrix, that is A. So this is how we are going to do the eigenvalue and eigenvector problems. So here I have shown you a non-symmetric problem. You can continue with a non-symmetric problem, and here you could find what you observed from the roots of this equation is it is 0, 1, 2. What is the characteristic equation we had? It is which resulted with eigenvalues is 0, 1, 2. Now you can find the roots which is distinct. None of the roots it is same. So here we found a case like under non-symmetric matrix the roots are not repeated. Non-symmetric matrix where which the roots are non-repeated. So under non-symmetric matrix we have a case like root may be repeated, and in symmetric matrix the roots may be not repeated and repeated. Like this we have some more problems to discuss in eigenvalue and eigenvectors topic.